This is our last video on our module on quadratic functions within the realm of polynomial functions. But we are going to work on doing what we wanted to do, or intended to do in the first place, which is apply this material, okay? So in terms of application problems, one thing I want to point out is this. We use quadratic functions to model many things. We can model profit or cost or area or, things acting under gravity or just like a, parabolic surface. But that being said, in application problems, when we're modeling things, we've often had data to begin with and then come up with some curve or rule that would model that situation, and it's not pretty, okay? It is not pretty numbers. We have something like, for instance, I don't know, let me make something up here, y equals ax squared plus bx plus c. Actually, we have a couple examples we'll go through here, but something in this form, y equals ax squared plus bx plus c, that is not in standard, not standard form. Fact of the matter is this: since they're so ugly, these numbers a, b, and c, they're definitely real numbers, but they're ugly. It's just really not convenient to complete the square and put it into vertex form because, let's face it, when you deal with quadratic situations, we're often looking for where the vertex of the parabola is, because recall that if you had a parabola that opened downward, it would have a maximum value. Okay, that'd be like, if you threw a ball in the air, what's its maximum height? Or, if you had a parabola that opened upward, like a minimum value, you'd have like minimum profit. You'd want to find where the vertex is. So what I've got for you today is a gem. But what it is right over here on the right side, we say the vertex of a parabola. And I can tell you right now where the vertex of this parabola is in general, so long as it is not in standard form, but more generalized form. We say ax squared plus bx plus c. If it is written like this, and all I need from you are the letters B and A. That's it. We don't even care about C in this instance. But I can tell you that the vertex is always located at this coordinate point right here, where we say negative B value over 2 times the A value. That is our X value of our vertex. Okay, and as a consequence, we say the axis of symmetry is some line. X equals negative B over 2A. Recall that the axis of symmetry runs through the vertex there. It's a vertical line. But we say that is the x value of the point of the vertex. And then to get the y value, we just say, well, if I knew the x value, I'd plug it in. I say, go find the function value at negative b over 2a. So a couple of notes right here. You'll see if a is positive, then our parabola has a minimum and is at x equals negative b over 2a. So this is our axis of symmetry here. We'll just plug that into the function to actually find the minimum value at that x value. And likewise, if our parabola opens down, that is if our leading coefficient or a value is negative, it's got a maximum, and it occurs when x is equal to negative b over 2a. And to find the maximum, we'd have to plug that into the function to find it. So, speaking of finding maximums, let's go ahead and take a look at this problem that I've got right here. We say the profit P, okay, in dollars for a company that produces antivirus and system utilities software. I know it sounds super fun. I thought so. It says is equal to this. P equals negative, here's the ugly numbers, right? Negative 2 10,000ths x squared plus 140 x minus 250 grand. And we'll say x is the number of units that we sell. Okay, but this would model our profit as the number of units we sell changes. Okay, what we want to do is find the sale level that will yield the maximum profit. So find the value of x that is going to yield the maximum profit. Notice I did not ask you for the maximum profit, even though we could find this. So according to our definition up here of how to find the vertex at any given time, given ax squared plus bx plus c is our rule, we'll just go ahead and do this. We say, in this instance, we say a is negative 0.0002. We have b, looks like in this equation is 140. And just for fun, just to see that we can identify this, c is negative 250,000 k. Okay, but the fact of the matter is this: we just want to know, okay, well, where, how many units would we have to sell? What level of sales would produce this maximum profit? And according to our definition up here, we just need to know x equal to negative b over 2a. We just plug these values in. It's super simple, guys. So we say negative b, so negative $1.40. Sorry, it's 140. And this is over 2 times the input of a. So we say this input here is negative 0.0002. Okay, so we're going to take a negative divided by a negative. Oops, that's a positive. And then we say 140 divided by 2 of these 0.0002s. Sorry to do some mental math here, but that is the same thing as 140 divided by we're going positive now. 0.000, double of what we had was 4. Okay, and so we'll just whip out a calculator here. We say 140. 140 divided by 0.0004. And what I can tell you is 350,000. What this is really telling us, we know 350,000 is x. This is the x value of the vertex, really. Okay, so we say our vertex is located at 350,000 units of sale, and then we'd have to plug that in to get the y value, the f value at that x value to get the y value. So this would represent profit at that x value, and this is just x. But in this instance, recall we said we just needed to answer that question. You need to sell 350,000 units to make your maximum profit. Okay, so that is a maximization problem. You notice that our parabola had a leading coefficient that was negative, and so it opened downward, had a maximum. What if we looked at a minimum type of application problem? And of course, we have this other function right here that is very, very ugly. As a matter of fact, I would like to rewrite it. So we probably should read the problem first. But notice that the leading coefficient will be positive, which means it opens up and has a minimum. So we say a textile manufacturer has a daily production cost of C, and C is a function of X, where C is total cost in dollars, and X is the number of units that, say, we produce at our business. Okay. Our question today is going to be how many units should be produced each day to yield the minimum cost, not necessarily what that minimum cost would be. In this instance, we are going to find the minimum cost by plugging it back in. But let's go ahead and start with this. How many units would I have to produce to minimize my cost, which, trust me, I am interested in. So I'm going to start by rewriting this. We say 0.0445, that's a 4, 5x squared, negative, this is a negative 110, minus 110x, and this is plus 100,000. Okay, so you notice that I just wanted to rewrite this so our leading coefficient was up front. But again, to answer this question, we just need to know where the vertex is. Okay, because if we want the minimum, it occurs at the vertex. We know this is at the point x equals negative b over 2a, and then f of negative b over 2a, or in this case, c of negative b over 2a. So let's go ahead and identify b. B here is, in this instance, negative 110. So we have negative 110. That's our b value. Okay, and over 2 times our a value, holy geez, it's not very big, 0.045. We end up simplifying down into this, a positive 110 on top, and a positive, let's see, if you doubled 45 cents, you had 90 cents, so, it looks to me like we'd have 0.090 kind of thing rocking. We'll go ahead and put this into the calculator, but again, before we do so, I just want to point this out. We are finding the x value of the coordinate, the x coordinate of our vertex here. Okay, so 110. How many times does 0.090 go into that? Well, if I hit the divide key, I can tell you. 0. Oh my goodness. Okay, so we got 1,000, 1,222, and roughly 2/5, a little bit bigger than that, or a fifth, excuse me. So in this instance, I said I wanted to find, okay, so what would that minimum cost be? And I know I didn't put that in the instructions here to go find this, but actually we can go and do this. We'd actually just have to plug this value back into the function to do it. But to answer the primary question, you would need to sell this many units or produce this many units to minimize cost. Min at this many units, okay? So now to actually go back and find this, we'll plug it back into the function. We'd have to get 0.045 times our 1222.22 repeating squared, minus 110 of those 1222.22s repeating, plus 100 grand. Okay, so I don't know. Let's do this in pieces here. We had to square this here, so times 1222.2222. And then it looks like we'll take that value squared times 0.045. So times 0.045 yield this value here. Okay. So now I have 2 calculators. We'll do this. That was minus 110 times our 1222.22 repeating. So we'll do that. 110 times 1222.2222. Whoops. Let's go back. 0.2222 repeating And just before we kind of sum all these together here, we say, okay, so we take this value here, 67222.222, minus 134.444. We get this here, and now plus this final, plus 100,000. So plus 100,000. And so we'd have a minimum cost of, like $32,700. But the fact is, these problems are super easy to do. All you need to do is plug these things in using this formula up here on the right. Cheers.